In this video, I will share how to derive an expression for potential energy stored in a stretched spring. For this purpose, let me consider a spring connected to a rigid support. Suppose I apply some force on this spring in vertically downward direction such that it gets stretched to some distance, means its length increases by some amount, suppose it is x. This has been obtained by applying some external force. Let me call it F external. Due to this external force, the spring has been stretched such that its length increases by amount x. This is the extension in spring. So we have to find how much potential energy is stored in this position. When we are applying external force on the spring, another force is developed inside the spring in opposite direction, and this force in opposite direction tries to change the shape of spring to its original shape, means this is called restoring force. Due to this force, the spring tries to restore its original configuration. So let me call this force as F restoring. Both these forces, F external applied and F restoring, will be equal in magnitude and opposite in direction. So mathematically I can write restoring force is equal to minus externally applied force. In magnitude of restoring force and magnitude of externally applied force will be same. Now how to find potential energy? For that purpose, I will have to consider a law known as Hooke's law. Hooke's law says the magnitude of restoring force is directly proportional to extension in the spring, that is x, and this proportionality is changed into equality by introducing a constant k. This constant of proportionality k is called spring constant or stiffness constant of the spring. Sometimes we call it stiffness constant. And the value of this constant depends on the material of which the spring is made. As I have earlier said, magnitude of restoring force and external force are same. A restoring force we have proved equal to k multiplied by x, where k is constant of proportionality and x is extension in length of the spring. So using this magnitude of external force, we can calculate work done, small work done during small extension. Let us suppose this small extension is represented by dx in this direction. Further, if I move through small extension, that is dx vector, from this point to this point, how much work will be done? So dw is equal to F external dot dx vector, because work is calculated as dot product of force and displacement. As it is clear that both F external and dx vector are parallel to each other, so angle between these two is 0. So we can write F external dx multiplied with cos of 0. A vector dot B vector is AB cos theta. After simplifying, I can write it is equal to F external into dx because cos 0 is 1. Now we have to put the value of x external from here. We shall get equal to kx dx. For calculating total work during this displacement x, I will have to integrate both sides. Integral dw will give us k integral x dx. K is constant, it can be taken out of integration. This will give us w is equal to half kx square. This work done during extension of spring length through x is stored in the spring as its potential energy. So the relation for potential energy of a stressed spring can be written as half k x square. This is the final relation for potential energy. Means to calculate potential energy of spring we need the amount of extension and spring constant, that is the property of material of the spring. That's all.